Any question about the material before we start? Everything is clear? Okay, so let's start our lecture. Today is our fourth lecture. In today's lecture, we will talk about more analyses than what we have seen so far. So far we have used Ohm's law, applied Kirchhoff's laws, uh, including the voltage Kirchhoff's laws and Kirchhoff's voltage laws and Kirchhoff's current laws. And we have seen how to assign the loops and based on the direction of the loop with the orientations of the voltage drops. And then we understood the relationship from Ohm's law between the current and the signs of the potentials for the resistors. We wrote KVL equations. We solved those equations for our unknowns. Today we will be looking at more advanced analyses, including the nodal analysis and the mesh analysis. Those ones are a higher level when it comes to tackling circuits with more complex topologies. In that sense, as we will see later on, those analyses can be solved using simultaneous equations or using computational softwares, including MATLAB, for example. And there are other solvers that are used also, and like PSpice, they also use those analyses to solve for the circuits. Uh, I will be clear with you. In some questions, I'll be asking you to use, for example, nodal analysis or mesh analysis. Some other questions, I'll be asking you to use of course, when it's if it's applicable and can be used. I would be asking you, for example, to use the KVL, KCL, and Ohm's law. Yeah, you're welcome. Okay, so let's get started with those analyses. In today's lecture, we will be covering the nodal analysis. So let's understand how do we apply the nodal analysis, or how do we derive those equations for nodal analysis, and then we will end up later on after we understand the theory behind it. We should be able to write those nodal equations by inspection. We will see how. Okay, so at the beginning, we will apply the nodal analysis with circuits that do not have voltage sources, and then the next step we'll see how do we apply the nodal analysis with circuits that have voltage sources. And next lecture we will be talking about the mesh analysis and with all the cases for the mesh analysis. So nodal analysis basically is a node voltage approach, which means those nodes that we have discussed earlier when we said that those nodes define distinguished electrical nodes. And now in this lecture, we will see how those electrical voltage nodes will be used to solve for the nodal analysis. At the beginning, we need to identify how many distinguished electrical nodes we have in our circuit, and then we will be assigning those nodes our variables. So our variables in nodal analysis approach are those voltages. So we will be assigning those variables V1, V2, V3, depends on how many nodes do we have in the circuit. And after that, again, here we were talking about uh, proving the nodal analysis approach. So we will be developing this those equations first, and we're showing you how did we come up with the nodal equations technique, how to write those nodal equations. So we're showing it to you from the scratch. Nodal equations are a KCL based, so we'll be relying on the KCL in order to derive those equations. And then once we identify those nodes, then the total number of equations we should be able to come up as n minus 1. So how do we do this? We will see. So where's the n minus 1? What about the one that we have skipped? This one is we call a reference node. This node, usually we assign it the ground, which basically a 0 volt. We will not include this equation. We will not write the KCL for that node. So that's why we will end up with n minus 1, because that equation for the reference is going to be a redundant equation. It's not going to help us. So let's see how we identify those nodes. At the beginning, if we have this circuit and we've been asked to write nodal equations for this circuit. Again, if we look at the nodes, the distinguished nodes we have in the circuit, we will see that we have the following nodes. We have this one. This is one electrical node, and that's why if you notice here we gave it V1. So this is one of our one of the variables. The second one is this one, and that's why here we gave it V2. We assigned it the voltage of V2. Now the third one was already assigned to me here to be the ground, the reference, my reference node, because at the end when I measure the voltage, I measure the potential with respect to a reference. So this is my reference that was given to me. And as you can see, this one has a 0 volt. Yes, go ahead. What's your question?
So basically, we're always taking the voltage at one node with respect to ground. So it's instead of me saying V at this node, it's V minus V ground.
Yes, our reference here, which is the 0 voltage, is I am measuring with respect to that reference. That's correct. The reference could be here. If the reference is here at this one, then I will be putting the ground right on here, and this will be the 0, and the other one would be the V2. But now here in this question, it was given to me that the reference is that. No, if you are given the option to pick the reference, you usually pick the reference with the branches that has the. We will talk about all the cases, but in this case, when I have uh, no voltage sources, I would pick the reference to be the one that has most branches connected to it. Okay. Here it was given to me that the reference is this point. I will continue with that case. Okay. Did I answer your question?
I think so, yeah.
Yeah. The second question.
I didn't have a second
No,
question.
is there any other students want to ask? Okay. So this is basically how we uh, pick the nodes, how we assign the voltages, the node voltages on them. And as you can see here, the number of the nodes is n equals to 3. So the number of the useful equations would be n minus 1, which is two equations. And that's why here I have two variables, v1 and v2, that I don't know. And I have, assuming that, of course, I know the resistors, I know the current in those sources, then problem is solved. Number of the independent equations is 2, number of the variables is 2, then the problem will be solved. So right at this node, node number 1 here, this one, which is basically later on I will be calling V1, I wrote the KCL. Now I1 here, this one is entering, this one is leaving. So I wrote minus I1 plus I2. I have those two currents, I1 small, I2 small leaving. That's why I wrote them as positive. So this is the first KCL equation at node number 1. At node number 2, so this is again, this is node number 2. This would be the KCL equation. I have I2 small entering. I have I3 small leaving. I have I2 capital entering. This is the KCL equation. So those are the two KCL equations for my circuit. I have, as I said, n minus 1 is 2. That's why I wrote two KCL equations. Now, the next step is using Ohm's law to substitute those currents with their equivalent expressions. So here, I know that I1 goes from the positive toward the negative, right? That's why I wrote I1 to be V1 minus 0 divided by R1. Again, I know R2 here, positive, negative, and that's why I wrote I2 equals to V1 minus V2 divided by R2. For the case of I3, I know that the current enters the positive, leaves the negative. That's why I wrote it as the potential difference across R3 is V2 minus 0, right? V2 minus 0 divided by R3 is indeed I3. Now take those three expressions, substitute them in the KCL equations that I found earlier. So this one and this one. Okay. Yeah, okay. So take those two equations, substitute I1, I2. I will rewrite those equations again just to show you. So at 1, what do I have? I have I1 leaving, I2 leaving. I have I1 entering, I2 leaving, 0. At 2, I have I2 entering, I3 leaving, minus I2 equals to 0. So those are the two KCL equations that we derived earlier. Now, if you substitute I1, I2, I3 in those equations, you will end up with the following two equations. Those are the nodal equations. So all what I have done so far was defining the number of independent nodes, assigning them our variables in terms of voltages, V1, V2, and then we wrote the KCL equations for those nodes. Then we substituted those uh, currents with their equivalencies using Ohm's law, rearranged, and came up now with two equations. As you can see here, our variables, those are our variables, the V's, the R's would be given, and the currents for the current sources are also given. So I have two equations with two unknowns. Problem is solved. You can solve them simultaneously and find the V1 and V2. So those are my nodal equations. Any questions so far about how did we derive those two nodal equations? Understanding where those two equations came from are extremely important for the next step. So once we agree upon the procedure that we did to derive or to come up with those two nodal equations, then writing the nodal equations later on by inspection would be extremely simple. Any questions so far about how did we come up with those two nodal equations? Okay. Okay, that's very good. So let's move now to the next step, which is we need to know how to write the nodal equations by inspection. This is extremely important and very useful and very time saving later on. So the procedure is as follows. At the beginning, find the n minus 1 nodes. So here, how many nodes do I have? Let me write or identify those nodes. So I have one here. I have one here. I have one here. And the reference was already assigned to me. So this is my 0 volt. I have two nodes that I need to assign the variables to. So let me call this one again V1 and call this one V2. So number 2, assign the node voltage variables. Here I have V1 and V2 since n minus 1 is 2. Now remember, I am dealing here with circuits that have no voltage sources. I don't have voltage sources. When it comes to the voltage sources, we will see the difference. Yes, what's your question? No, no. N is the total number of nodes. Now look how many number of nodes do I have here? I have the red, I have the green, I have the blue. So here N is 3. N is the total number of nodes. Okay. So we assigned our variables. Our variables are the node voltages. I have V1 and V2. Now we come to the writing the nodal equations by inspection. That's the third step. We stand on the node of interest. Let's say here V1. Then we cover all the branches that have resistors by writing the potential difference divided by the resistor. So how do we do this? So we are here. We are standing on V1. Then we go the following. V1 minus V2 over R2. So we write nodal equation at V1. So we go V1 minus V2 over R2. So we finish the first resistor. Then we go V1 minus 0 over R1, of course, plus V1 minus 0 over R1. Then we look at the current from the sources. The ones that are leaving, we write them as positive. The ones that are entering, we write them as negative. So here, minus I1 plus I2 equals 0. Now let's do the same for nodal equation. Now this time we will be standing on the V2. I'll make this one in different color. Now I am here standing on V2, and I will be covering now all the branches that have the resistors. So I will go V2. I'm starting with the one that I'm standing on. So I go V2 minus V1 over R2 plus V2 minus 0 over R3. Oh, was different color. Okay. Plus V2 minus 0 over R3. Now we look at the current sources. I2 is entering that node that I'm standing on, so I write it as minus I2 equals to 0. So those are the two equations. Now, if I compare those two equations with the one that I got earlier, V1 minus V2 over R2 plus V1 over R1, V1 minus V2 over R2 plus V1 over R1 plus I2 minus I1 plus I2 minus I1 equals to 0. Let's look at the second one. V2 minus V1 over R2. V2 minus V1 over R2 plus V2 over R3 plus V2 over R3 minus I2 equals 0. Minus I2 equals 0. So this is how I write nodal equations by inspection. And as you can see, this is going to save me a lot of time when it comes to writing those nodal equations. So any questions so far about how did we write those nodal equations by inspection?
Sir?
Yes.
So basically, you draw your nodes, declare each node equal to a voltage. You write the KCL for each node, for example.
Can you reduce the TV's volume, please, so we can hear you?
Sorry. Mom, can you go somewhere else? I'm not. So you find your nodes, declare a voltage for them, write the KCL, and swap the currents with delta V over R, whichever one that is.
Yes.
Okay, thank you.
And then Matthias, we came out with this procedure, which is basically saves all what we have done to write those nodal equations that we have derived earlier. We've shown you how did we derive those ones. Now we have this procedure where we can write the nodal equations exactly the same way, however, by inspection, which has saved us some time of distributing those currents, writing the KCL, substituting those currents with their equivalent Ohm's law expressions. By inspection, we did it in one shot. Does this make sense?
Yes.
Okay. So this is the easiest way to write nodal equations by inspections. And again, we said that so far we have not talked about circuits that have voltage sources, only circuits that have current sources. We will see why in few slides. Now let's do this example. In this example, a circuit was given to me, and as you can see, I don't have voltage sources in this circuit, and I was asked to calculate or find the value of V1 and V2. So in this circuit, the reference was already assigned to me. The variables were already assigned to me. I will only highlight those nodes that V1 and V2 are assigned to. So I have, this is the first node that V1 was assigned to. I have the second node that V2 was assigned to. And then I have the reference node that 0 voltage is given to because it is our reference. So that's the 0 voltage. So in other words, the nodes that I will be solving for were already given to me. I just need to write the nodal equation. So let's do this. Does anyone want to try giving me the nodal equation? Anyone wants to try and find the nodal equation for me? Okay, think about it. Think about it. I'll give you a few minutes.
Sir,
Yes, go ahead.
I got the equation for nodal analysis at V1.
Okay.
Yeah, so
Go ahead. Tell me what's the equation. So we're here, nodal equation at V1. Okay, go ahead.
okay, so V1 minus V2 over 2 ohms plus V1 minus 0 over 10 ohms plus V1 minus 0 over 5 ohms, and then plus 6A equals 0.
Absolutely. That's correct. Okay, that's very good. This is very good. So you have, so far you have demonstrated understanding to how to write nodal equation by inspection for that circuit that doesn't have voltage sources in. We are going to write the nodal equation at V2. Anyone else wants to try his luck and give us the second equation for V2?
I can try V2. So I think
Okay, go ahead.
nodal equation of V2 would be V2 minus V1 over 2 ohms
Okay.
minus 6 amps plus V2 minus 0 over 4 ohms
Right.
minus 3 amps equals 0.
Yes, that's correct. So those are the two equations, and as you can see here, if we now rearrange those equations, we will get, so let me say this is equation number one, equation number two. So from one, we have V1 minus V2 over, if I multiply by 20, what do I get? So this becomes 10 V1 minus V2 plus 2V1 plus 4V1 equals 2 minus 6 minus 120. So this is the first equation. Now this one becomes 10V1 plus 2 plus 4, 16V1 minus 10V2 equals minus 120. So this is the first equation. Now for the second equation from 2, I have here, if I multiply by 4, I get 2 V2 minus V1 minus 24 plus V2 minus 12 equals to 0, right? And now this one would be 2V2 plus V2, that's a 3 V2 minus 2V1 minus equals to 36. Now we need to solve those two equations simultaneously and find the okay, I'm reading your questions here. Apparently you've written some questions.
Sure. Is it okay if we use a different convention for nodal analysis?
Well, to make it easier, I think we need to stick to this convention of the nodal analysis. When it comes to the when it comes to the KCL and KVL, you can choose the direction that you want, but for the nodal analysis by inspection, let's just stick with this convention. We are right on that node, and then we go for the branches that have the resistors. We write the potential difference divide by the resistance of that resistor, and then we look at the current sources. Current sources that are leaving that node are written as positive. Current sources that are entering those nodes are written as leaving as positive, entering as negative. Now here, let me write down those two equations. So we continue solving. We have 16V1. Feel free to try solving those two equations as well. It's a good practice while I'm solving them as well. Minus 2V1 equals to 36. So we have here 16V1 minus 10V2 equals to 1 minus 120. We have minus 2V1 plus 3V2 equals to 36. Now, if I multiply the second one with 8 and add it to the first one, what do I get? So I have here, this one would be 0, right? And then I have 24 minus 10, 14 V2. Then I have 36 times 8 minus 120, 168. Then V2 is 12 volts. And take this one. Let me call this one 3 and substitute it either in the first one or in the second one. Let's substitute it here. So we said that if this one is 1, 2, right? Now 1, 2, call them as 3. This is 3, 4. So this is 5. 3, 4. So 5 and 4 is going to be minus 2v1 plus 3, 12 equals to 36. Then I have here v1 equals to 0 as well. So this is how we solve the nodal equations for a circuit that does not have voltage sources. If you have any question, please go ahead and ask. Did I miss any of your questions? There were several questions here. Right. Okay. So again, the nodal analysis is a KCL based, and if you notice, when we wrote the nodal equation by inspection, and we were standing on V1, we were going V1 minus V2 divided by R. This is a current. In other words, we're looking here at all the summation of the currents, but this is done in a very nice and simple way that we're calling here. We're calling it here by inspection. But we have shown you that if you go the conventional way, which is basically putting the currents first on the circuit, writing KCL, substituting those currents with their equivalent expressions, you would be getting at the end this exactly the same results of the inspection.
Sir, how do you get minus 120 and 36?
Minus 120 and 36. If you go back to the nodal equation, I have the current. When I wrote the nodal equation at V1, I had the 6 ampere leaving. That's why I wrote it in my equation as a plus 6. When this current went to the other side of the equation, became minus 6. Now, remember here, I multiplied the equation. I multiplied the equation with 20. So here, I multiplied it with the 20, right? So 1 times 20. Equation number 1 times 20. It gave me 10 V1 minus V2 plus 2 V1 plus 4 V1 minus 120. I multiplied by 20. I could have multiplied by 10. Even it doesn't matter. It's not going to matter, right? Make sense? Even if you multiply by 10, what you're going to get here is basically 6v1 minus 5v2 minus 60. It's not going to matter. I picked up 20. It could have been 10 also. Any other questions about nodal equations or nodal analysis, how to write the nodal equations, and how to solve for nodal equations by inspection?
Sir, what did you get for the voltages again?
I got V2 equals 12 volts and V1 0 volts.
Okay.
Did you manage to get the same answers?
I'm still going from my calculation.
Okay. So again, I have written the solutions for you here in the next slide. I mean, the formulations of the nodal equations. Here you have them here. Now let's move to the next case. Next case is when I have voltage sources. Why having voltage sources are different? Well, because now those voltage sources, they exhibit constant voltages, and they are also in contact with those nodes, so they will be somehow affecting the way we write the nodal equations. Now, if we look at this circuit, for example, here in this circuit, let me identify those nodes. I have this node. This is node number 1. If you want to call it number 1. I have this node that I'm calling it number 2, and that's why you can see that I have assigned, or the question has assigned V2 to it. And then I have node number 3, which is this node, and it's assigned V3 to it. And then I have node number 4, and this node number 4 is the 0 voltage. So in other words, if I am now to summarize what I have here, I have n equals to 4, and that's why n minus 1 is 3. Okay? N minus 1 is 3. So just looking at this number, you would make you think that you need 3 equations to write the nodal equations for this circuit. In reality, no, you don't need 3 equations. Why? I'll tell you why. Remember when we had the current sources, we did not know those voltages. Those voltages were variables to me, right? In the case where I have a voltage source here, notice what did this voltage source, what did this 10 volt do to my variable V1? Can somebody tell me, what did this 10 volt voltage source, what did it do to my variable V1? I had originally, if I am to look at my number of the n minus 1 equations, there are 3 variables, 3 nodes, 3 variables. I'm giving them V1, V2, and V3. But can somebody tell me the existence of the voltage source this way, what did it do to my V1? Absolutely. Because the voltage here between the 0, again, remember the definition of the voltage source. The voltage source, what does the voltage source do? The voltage source creates potential difference between its 2 terminals. So it depends on what you apply on one terminal. The second terminal will be abided by this that you applied on the first one. So here, I assigned, or I put this negative terminal of the 10 volts to the ground, to 0. This means the second terminal will be 0 plus this voltage difference that this voltage source is going to generate, which means, and in this case, my V1 now is not variable anymore. My V1 now becomes known. So the existence of the voltage source that is connected to one of the variables, and it's the second terminal connected to the ground, which is 0, which is defined, which is given to me, made that voltage at that node known. So it is not variable anymore, which means, look at the number here, reduced from 3 to 2. Why? Because I don't need to write the nodal equation anymore at V1. V1 now became known. V1 now is 10 volt. So that reduced the complexity, that reduced the number of the equations that I need to write.
Sure.
So this, yes, go ahead.
So you're saying like V1 and V2, for example, can form one supernode.
No, I haven't talked about the supernode yet. I am coming to the supernode, Right now, I'm only talking about a voltage source that is connected between the reference point and my variable node voltage. So that voltage source that is 10 volt that is connected between my reference and my variable V1 made that variable known. It's not variable anymore. Now it becomes 10. Does this make sense?
Yes.
Okay. Yes, the reference node is the same as the ground node. That's correct. And that's why I gave it 0 volt here. So that voltage source, that this voltage source creates potential difference. It generates a potential difference of 10 volts across its terminals. Since one of its terminals is 0, then the second one would be 0 plus 10, which basically means that this V1 now is 10 volt. So this is what that voltage source did to my equations. It helped me find one of those variables. Now, on the other hand, I have now this voltage source, the second voltage source, that is not connected to the reference. It's not connected to the reference. So what does that mean? Back to the definition of the voltage source. The reference node is always 0. And to answer your question, in the case of non-zero, we're talking now about this 5 volt. Look at the 5 volt. The 5 volt source is not connected to the reference. The 5 volt voltage source is connected between V2 and V3. V2 and V3. What does this mean? Remember how did we define the voltage source? We said that the voltage source creates potential difference between its two terminals such that the one that has the plus is higher than the one that has the minus. You're absolutely correct, which means no, it's V2 minus V3 equals to 5 volts. V2 minus V3 equals to 5 volts. So this voltage source bounded those two variables, created a voltage condition basically between V2 and V3. Since it generates a potential difference of 5 volts, and I put the negative terminal of this 5 volts on the V3, and I put the positive terminal of the 5 volts here on V2, basically this means that the voltage at V2 will be greater than the voltage at V3 by 5 volts. Why? Because this is what this voltage source 5 volt has done. It created a relationship, fixed the potential at V2 with the potential at V3, such that the potential at V2 is always greater than the potential at V3 by 5 volts. If you want to understand this further based on how did we define the KVL, take a KVL equation here, take a loop and write the KVL. You will find that the voltage, now V2, remember V2 is here. Remember V3 is here. If you write the KVL, this loop, you will see that it's entering V2. plus 5 because it's entering the positive terminal, plus V3 equals to 0. And if you move now V2 and V3 to the other side, you will find that V2 minus V3 is 5. So this basically supports the idea that we have just introduced, that this voltage source creates a potential difference and it binds the voltage the variable at its positive terminal to the voltage variable at its negative terminal, and that's why V2 minus V3 equals to 5 volts. Is this understood? Those are extremely important uh, points that we will build the supernode on. Now, the supernode later on is going to become an easier to understand. Why? Because the definition of the supernode, once this voltage source creates a binding expression between two of the variables, now I can treat those two variables as one big node. Why? Because there is an already binding condition between V2 and V3, and I will now treat it as one big supernode. So treating it as a one big supernode, how does it, how can we write this supernode? I did not say V2 is positive. What I said that the 5 volts created an expression, a binding expression between V2 and V3, such that V2 is greater than V3 by 5 volts. So to give you an example, if V2 is 6, then V3 should be if V2, let's assume V2 is 6, then V3 should be 1, because the voltage source basically says that V2 should be greater than V3 by 5 volts. So if V2 is minus 2, then V3 should be minus 7. I'm just giving you an example. So keep in mind, this is the definition of the binding expression here between two variables. I have two variables, and now I created a binding equation, a binding condition, such that one voltage is greater than the second voltage by this amount of voltage, which is what the voltage source is generating. Now let's go back to the supernode. In the supernode, I will be treating that supernode this way. Number one, I would be making a dotted circle such that I intercept all the branches that are connected to the variable V2 and the variable V3. So in this case, notice that this dotted circle, is intercepting with all the branches that are connected to V2 and V3, such that it encapsulates that voltage source and any other branch that is connected in parallel with this voltage source. Right? So let's assume if I have a resistor here, this resistor would be inside that dotted circle. So I draw that circle, that dotted circle, right? And then I after I draw this dotted circle, I identify the branches that I have intercepted. I have 1, 2, 3, 4 branches. Those 4 branches are connected to resistors. So that's why when I want to write the nodal equation by inspection between V1 and this supernode, I will call this one Sn. So writing the equation at the V1, for example, and I would like probably to insert here. So just a second, let me. So let me draw the circle, the circuit again here. So I have
Sure.
yes.
So you're saying if we threw a voltage source into a circuit, you treat that node where it is like it's just one giant node, and everything, and it takes into consideration everything going in, everything going out.
Yes. Yes, I'll show you how to write nodal equation for the supernode in a second. Let me just finish this one. So we have here 8 ohm, 6. So this one was V3, this one was V2, and this one was V1. So we said that we draw a circle, a dotted circle, such that I made it to intercept with all the branches that are connected to V2 and V3. So notice how many branches I have: 1, 2, 3, and 4, right? Now I will write the nodal equations by inspection. So let me first start with the first node at V1. So nodal at V1, it would be, again, I don't need to write the nodal at V1, right? Why? Because I know now V1 equals to 10 volts. See, this is the beauty about having a voltage source connected to the reference and connected to my variable. So pay attention to this, keep this in mind. Now I need to write the nodal at the supernode, which is this one. Now the supernode here, as you can see, it has 2 sides. One side is V2, the second side is V3. So when I am here, I would be jumping between those 2 points. So at the beginning, I will be standing in here. And then I would be writing all the expressions that are related to V2. So I would go, let me choose another color here. V1 minus V2 minus V1 over 2. V2 minus 0 over 8. And then I would jump to the next variable, and I will write V plus, of course, all this in one equation, plus V3 minus V1 over 4 plus V3 minus 0 over 6. So this is how I'm going to write now the nodal equation. So it would be I am now at the beginning, I am here on V2, so I will go V2 minus V1 over 2. And I'm keeping my eye on the branches, right? I said I have 4 branches that have resistors, so it would be 4 fractions here, plus V2 minus 0 over 8, plus now I will jump to the other side of the supernode. I am right now on V3, so plus V3 minus V1 over 4 plus V3 minus 0 over 6 equals to 0. This is the supernode equation. I'm done with the supernode equation. Now, the second supporting equation that I need not to forget, because at the end, I do have 2 variables. One equation is not going to help me. There is a second supporting equation. Where does it come from? It comes from this binding condition that we have talked about, which is V2 minus V3 equals to 5 volts. So those are the 2 equations. Now here remember V1 is 10, so it's not a variable. It's not a variable anymore. It's known. So I will end up with 2 equations, 2 unknowns. Problem is solved. Don't let it scare you. No need. Supernode is very simple. Supernode, it is the 2 variables that are connected with a voltage source in between. When you write the supernode equation, nodal equation, it's no different than the one that you have seen earlier, except that you jump. You finish the first variable, and after you're done with the first variable, you jump to the second variable that is within the supernode equation. Supernode, you know, variable, the second variable in the supernode, and you continue writing the expressions in the same equation. And then the second equation would be the supporting equation, which is V2 minus V3. Now, if you rearrange now those 2 equations, what you're going to get, you have here V2 minus V1 over 2 plus V2 over 8 plus V3 minus V minus 10. So I'll write them right away. 10 minus V3 minus 10 over 4 plus V3 over 6 equals to 0. So this is the first equation. If you multiply by 8, so this is equation number 1. This is, you put this one as number 2, and this is number 1. And then if you solve those 2 equations, you should get the answer for V2 and V3. So 2 times 8, what do you, so we have 4 V2 minus 10 plus V2 plus 2 V3 minus 10. Let's think 24. Let's take this one as 24 by 24. So you have here 12. You have a 3. And you have here 6 plus 4 V3 equals to 0, then 12 V2 minus 120 plus 3 V2 plus 6 V3 minus 64 V3 equals to 0. Then you have here V2 12 15 V2 plus 10 V3 equals to 180. So this is equation number 3. Now solving V1 and V3, if you take V2 equals V3 plus 5, substitute it, you should be getting the answer to that equation. Let's see here. Okay. So we have here 15 V2 plus 10 V3 120 V2 minus V3 equals to 5. You can multiply this by 10 if you want and add it. So here 10 V2, 15, 25 V2 equals to 180 plus 50 is 230. Then V2 is 9.2 volts. So V2 is 9.2 volts. Substitute in here. Then V3 is V2 minus 5. V3 is 4.2 volts. Supernode is used whenever you have a voltage source that is connected between two node variables that neither of them is a reference. So it's creating this binding equation between two variables. Whenever you have the voltage source connected between two variables, then you have a supernode. Okay, so this is how we solve the supernode. As you can see, what we have here is we have two examples. I'll let you work on those two examples. The solutions are there, and maybe we can revisit them later on during an office hour or during a question sessions, or maybe at the end of the nodal analysis and the mesh analysis, we can have a session where we address your questions about the material. But as you can see, this question is a question that combines current sources with a voltage source. And notice here, just to give you the heads up, the voltage source here is connected between two variables. So it's not connected to the reference. That's why you have a super node. And where is that super node? The super node is this. Remember, we said that that node, that super node, is going to have or include or enclose that voltage source and any element that is connected in parallel with that source. So when I write the super node here, let me do that very quick in the remaining 2 minutes. If I want to write the super node here, what do I do? I have here how many? I have two resistors, four branches in total, two resistors and two currents. So nodal equations at the super node would be again V1 over 2. I did not write 0. I did not write V1 minus 0 because now we know it's a reference V1 minus 0. It's V1 over 2 right away. Then I have the 2 ampere entering, right? And then I'm done. I'm done with those two branches. I'm done here. Then I jump to the second variable and I have two branches. So within the same equation, plus V2 over 4. I have the 7 leaving, then plus 7 equals 0. So this is the supernode equation. What is the second supporting equation that helps me in solving for this circuit? It is the binding expression between V2 and V1 due to the 2 volts. So what do I know? I know V2 minus V1 equals to 2 volts. Two variables, two equations, problem solved. So this is done. See, in 1 minute, we wrote the nodal equations in 2 minutes, to be honest with you. This is the detailed solution. Here is another question. Maybe I'll leave that to you. This one, the reference is not given to you. You can pick the reference point wherever you want, but keep in mind that if you don't have the reference connected to one side of the voltage source, then you have a supernode, right? Here you have a supernode. If you write the equation, if you put the reference here, then you don't have a supernode. Okay, thank you so much. I'll let you go through those ones. The solution is given to you here, and we'll see you next week. Have a good weekend. Thank you. Bye.
Sure.
Yes.
Could we actually re-examine our original supernode?
Do we have to what?
Is it okay if you go back a little so we can re-examine our supernode?
Sure.
Our first one we did.
Sure. Yes.
So basically, when you're creating a supernode, you're basically taking these branches and converging them on the 5 volts and treating that as a node.
I took the two variables that have the voltage source connected between, and I made a super circle. That circle basically encloses that voltage source and any other element connected in parallel with that source. So right here, that voltage source does not have any other element in parallel. However, if you look at this one, this question, it does, this one, the supernode does have the 10 ohm connected in parallel with the voltage source. That's why I had that 10 ohm inside this supernode.
So the supernode is basically being treated like it's any other node.
Exactly, no difference, except it has two variables. It has both variables that I'm writing the equation for in the same equation.
Okay.
So go back to this example 2. Try to write the supernode equation by yourself.
So a supernode has its own equation.
Right. Try practicing several questions that have supernodes to see how, how, if you understood the supernode well or not.
Okay.
And then we can discuss it later if you want.
All right.
Make sense?
Okay. All right. Thank you, sir.
Thank you. Have a good weekend.